Alright. So let me catch up to a little bit here. So obviously for this, what's N? 14. And P? Thank you. Yeah. So 50-50 chance. So let's probably get exactly 9 heads out of 14 times. How do I set that up? Good. 14 flips. Choose 9 of them to be heads. Good. And some of you guys might realize that the situation where P and Q are equal, they're both 0.5, this is always going to be 0.5 to the 14th then, right, in this case. Doesn't really matter which is which. You're going to end up with 14 of them. If you don't get that, it doesn't change anything. So it's all good. What do you guys get when you do that? Let me remind you what it looks like. You get what now? Sweet. 14, choose 9. 0.5. We'll just go ahead and put it all in there. Yeah, 0.1, 222. Okay, I like it. So about a 12% chance to get 9 heads out of 14 flips. So that would not be unusual. How do you do this shit? I think, hopefully, let's see if I've discussed this idea enough. How do you do that? Huh?
You do the none.
Yes, you do the probability of none. And then do 1 minus that. So you do the opposite of what I asked, and then I go, and then you go 1 minus that. So you actually answer the question. Anytime the opposite situation is easier, I'm going to do that shit. Yes? Yeah. So the only way to have none is if they're all 0.5. Which is kind of funny. If they're all tails, there's no heads. If they're all tails, that's 0.5 to the 14th. Yeah. Now again, if you set up the whole thing for no heads, it would be, this is equals 1 minus that. It would be 1 minus 14, choose none, 0.5 to the 0, 0.5 to the 14th, and like we discussed yesterday, this is 1, so it is just this piece. But again, it doesn't matter if you don't realize that. You can set up the whole formula. It's going to come out right. So 1 minus... Oh yeah, look at that yumminess. So if I do 1 minus that, I get 0.99994. Is that cool? You guys see that? See how I avoided having to deal with this at all because I knew I had to do 1 minus it anyway? So I'm not going to worry about how ugly it is until I get the actual answer. And the actual answer, sweet, I can just write that down. So pretty much, now watch. What is this? Right there, if I flipped a coin 14 times and I didn't get a single head, they were all tails, is that likely to happen? What's the chances? Yeah, probably I get at least 1 head is almost 100% chance. So if I take a coin that somebody tells me is a fair coin and I flip it 14 times and get nothing but tails, is that impossible to happen? No. Is it evidence that something's wrong with that coin? Try again. The probability I don't get a single head is 0.00006. So if I don't get a single head, was that likely to happen? This is really important. You gotta stay with me now. If somebody says, let's see, how is this? somebody says, I can make all my free throws. And they miss a free throw. That's evidence that they're wrong, obviously, right? But this is more a case of, if it is a fair coin, I expect to get at least one head out of 14. There's almost 100% chance of that happening. What's the probability that I don't get any heads show up on it? 0.00006. That is really, really unlikely. So what's more likely? That just happened by chance? Or something's wrong with that coin? Yeah, that's evidence. Now, is that proof that something's wrong? No, that's the no. Is it evidence that something's wrong? Yes. Especially if I keep going and I still get nothing but tails. You with me? So there's a real distinction between, is it impossible for that to happen, to get no heads? No, it's not impossible. Is it really, really unlikely? Yes. Right?
Is it possible like one of those coins where it's the same on both sides?
Could be, yeah. In which case I could have just looked at it. But you're right. There's something that maybe they weighted it a certain way, and again, it's not proof. You can't prove anything with this. But it's really strong evidence. Okay. Maybe. The thing about flipping a coin, people instinctively think the coin has a memory. So if I flip a coin and it comes up 3 heads, does the probability the next one is a tail increase? No, but sometimes you say no to that, but sometimes in our head we act that way. Well, it's done this. Has anybody ever seen, okay, I don't know if any of you guys even play the lottery or anything, but very often they'll list numbers that have happened before because they're assuming they're less likely to happen again. So like, oh, I haven't gotten to 15 in a long time. But if they're just randomly picking them every time, and I'm not going to get into any controversial, maybe they're not. If they are, then every time they do it, anything could happen. Doesn't matter what happened before. That's why flipping 14 tails is not impossible, right? Because every time I flip the coin, it resets. It's 50-50. But if I do get 14 tails in a row, that is starting to become evidence that something's wrong with that coin. Either it's got nothing but tails on both sides and I just didn't look, right? Or it's weighted or something. Okay, maybe. Today seems to be Jeff just going off on problems like crazy. All right. I put in the middle here something about how to do these in your calculator. I am really not concerned at all that you're able to do this. This is just another thing. If you want to do it, you can check your work. Yes? So if you do, let's do this together. So if you do distribution, see that right there? And if you hit second vars, you get into the distributions. And the first couple, they're normal distributions. That looks cool. Might come back to that later. Now if you keep on going down, you'll eventually see binomial. I'm not going to spend a ton of time on this, but I'll show you one example because I don't give a shit if you're able to do this. But if you want to, you can do this and check your work. The difference between these two is this is binomial particular, this is binomial cumulative. So if I want to know the probability I get exactly 9 heads, I use this one, particularly 9 heads. If I said I want the probability that I get at most 9 heads, that one, that's cumulative. And remember what cumulative means, it adds all the way up to a certain point. So if I want to redo that first one we did, binomial particular value. If you have the newer calculator, it does this. If you have the older one, hold on, I'll show you what it looks like. So 14 trials, that means 14 flips. 50% chance of success. And I want to know the probability I get 9. So in the older calculator, it would just show up binomial PDF, parenthesis, and you would put N, comma, P, comma, Q. I'm sorry, not Q. N, comma, P, comma, X, how many successes you want. Why do I not have to tell it what Q is? It's a freaking calculator. It can calculate it based on what I say P is, right? And now you understand why you have punctuation on your calculator. So let's see if it gets 0.1221, blah, blah, blah. Yay. I like it. So that's just a nice little quick way you can check what it looks like you got. What I really love, and that's said very sarcastically, is when somebody sets the equation up completely wrong, but then the right answer shows it. That's awesome shit. You're going to lose most of the points. All right. Okay. All right, so that little middle section is, if you would want to, you could try this out and see if it comes out okay. Now this middle section is old news. This one right here is semi-new news. I mean, remember, this is how to get the maximum expected, the maximum usual, and minimum. How do I get the mean? Yeah, so 14 times 0.5, so I expect 7 heads. And now I can start to, and if I calculate the standard deviation, this whole thing is going to be, I expect 7 heads. But if I got 6 heads out of 14 tosses, I'm not going to go, oh my God! So this next step is trying to build up how far away from 7 until I start to get freaked out. So standard deviation, 14.5.5. So square root of 3.5. I get 1.871. So now take a minute and calculate these. The minimum expected, the maximum. That helps out in a few places. What is this again, this number that's up here? What does that represent? Standard deviation. And I want 2 of those, right? And if I, now you don't have to do this, do you understand? You don't have to do what I'm going to do. I just want to show you some of the neat stuff with this calculator. You see this kick-ass button right there, stow? I want to stow that shit. So stow. In X, there's my most immediate variable button. Do you see if you hit alpha, you have all these variables you could use, A, B, C, D, blah, blah, blah? I'm just going to use X. So now X has that in it. And I want to take the mean and subtract that, and I want to take the mean and add that. Now again, I got the same answer some of you guys got, right? Yes. Did you have to know how to do this? No. Is this kind of cool? Will it maybe help in the future? Yeah. So I don't have to write a bunch of freaking decimal shit then, right? Okay. So we get, for the minimum, we got 3.26 roughly, and for the maximum, we got 10.74. So would it be unusual to get 10 heads officially? No. Would it be unusual to get 11 heads? Yes. So technically, if I got 11, 12, 13, 14 heads, that is evidence that something unusual has happened. Notice how I say that. It's not necessarily proof of anything. I'm not even saying that the coin is weird. Just that's proof that that's evidence that something unusual has happened, and that one explanation might be somebody did something to the coin. Okay. Now, notice this. All right, so tell me the possible values for x. Up here I used 9. Well, what are all the possible values for x in this problem? 0 to 14. Yeah, I can get 0 heads all the way up to 14 heads, right? So this is a table where I've calculated, actually I had a computer calculate all the possibilities. And look, we did it for 9, right? And look, bam. It rounded to 3 places, but that's what it is. You with me? You guys see that connection? So the probability I would get 6 heads is 0.183, so forth. One little thing I want to point out now that's going to come back later is this symmetric?
Yeah.
Why is that not surprising?
Because it's 50-50.
50-50. Beautiful. Perfect. It's always going to be symmetric. It was 50-50. Let that sink in. That should make some sense. Even more special in this case, does that look normally distributed? Right? Thankfully, I chose the right side. So it totally looks like it could be normally distributed. We're going to come up with a way to, oh my God, what I just drew doesn't. We're going to come up with a technical way to identify if this is normal or not. Not today, I just want to lay some groundwork today. Okay, one thing to realize is, where's the mean on this picture? The mean was 7, there it is, right? What if the mean had been 1? Would there have been a chance for it to look normal? It would have started high and went low. It would have looked skewed right. It wouldn't look normal. So it looks like one condition seems to be somehow the mean has to be closer to the middle. You can't be close to one of the walls. All right, so I'm going to bring that up later when it becomes important, but there is a technical way to determine if an NPQ situation is normal enough. Maybe. We don't know that yet, so don't freak out. Now, so look at the very top of this. What I'm trying to do with this sheet is I'm trying to get us to build off of what we know from chapter 4 into what we're about to get into. The big difference between chapter 4 and chapter 5 and 6, let me see if you guys can get this. What kind of data do I have up here? Discrete or continuous? What's happening in this problem? What am I doing? It's going to be discrete because I'm flipping a coin and looking at the number of heads. Could I get 4.786 heads? If you can, you got to show me that. It seems like it would be kind of neat. Is everybody with me? A little bit? So this is discrete. Binomial is definitely an example of discrete. The XP of X shit is definitely discrete because I put the values down. I couldn't do that for a continuous one. That would take me for the rest of my life and the rest of my kids' lives and the rest of their lives and the rest of their kids' lives. Right? Because there would be an infinite number of possibilities. That's that. So these two things we did in chapter 4 are discrete distributions. We're about to take the step into continuous distributions. Oh shit. So notice this. Looking at the chart in this table, what was the probability that at most 6 heads happens? How would you get that? What does at most mean? Look here, at most gives people trouble. There could be at most 6 people in an elevator. So what does that mean? If there could be at most 6. 0 to 6, right? That 7th person, you're like, what the hell? Okay, maybe. So can you figure out the probability of at most 6? You don't have to do a lot of work. You already have all the numbers. You just have to put them together correctly, right? What would you do?
Add all up.
Add what up?
The numbers from 6 to 0.
I like it. Just add those up, right? Kick ass. I think it comes out to be 0.395. You come with 3. You can look at it, Jeff. There you go. Okay. So that's that piece. So that's 0.395. I'm going to come back to that later if I have enough time. There's something we learned in chapter 6. What did we say? This looks normal. Chapter 6 is what to do with a normal distribution. So there is a way to use what we do with normal distributions to calculate this a different way. So I might come back to this if we have time. Now watch this. What is the probability of exactly 7? for example. 0.209. What is the area of this rectangle? Oh. What's the width of the rectangle?
Standard deviation.
No.
Like the number.
1, right? What does this rectangle go from to? Let's try that. Where does it start?
6.5.
6.5 up to?
7.5.
All right, so it's definitely got a width of 1, right? And how tall is it? 0.209. So what's the area of the rectangle? Why is that a hard question? What's the area? 1 times 0.209, so 0.209, right? All right, so this is a very minimal example. I'm going to do a couple more examples of this, but when I have a picture of a probability distribution where the whole area is 1, then any piece of it is related to the probability of that happening. So what's the area of this piece? 0.209. So what's the probability of this happening? 0.209. So, let me do this. You guys know about darts, right? If I say darts, I don't mean lawn darts, where they had to stop making that game because people are throwing it in people's heads and stuff. It was not good. Oh, Jimmy just got a dart stuck in his head. That's not good. I apologize if that happened to anybody. So darts, you have a bullseye. All right, I'm not going to draw the whole thing. And then you got these little triangular pieces coming off of there. Right, oh my God, we're supposed to be about the same height. All right, now all the way around. Okay. Now, I suck at darts. So, if I were looking just at the darts that actually hit the board, not the ones they hit there, my little brother's head. Ow. Right, don't stand over there. My poor little brother. I have no idea how he grew up. So just looking at the ones that hit the dartboard, what's the probability? And I'm just throwing. And I suck. I have no skill at all. So I'm just throwing them, just wailing away at it. What's the probability I get in here would be equal to the percent of the area that is, right? So if there were, let's see, how many is that? 1, 2, 3, 4, 5, 6. I like it. So if there's 12 triangles in there, what's the probability I get into any one of them? 1/12 of that, because that's 1/12 the area of the whole thing, right? So what if the area of this was, I don't know, 2 somethings, and the area of the whole thing is 30 somethings? What's the probability that I hit right on the bullseye if I'm just like throwing them like crazy? 2 out of 30. It's the percentage of the area. It's how much area that is. Okay, no. So,
Isn't it usually circles?
no. The triangle's coming up. Yeah. Circle in the middle. Okay.
I've never seen a dartboard like that.
All right, Google. So what we're getting up to is, how do I say this a different way? Let me think. How else to? I love that dartboard method, but it looks like you guys didn't like that too much. Yeah. Okay. So say I'm playing some weird game where I've got these squares here, and if I throw like a little
Beanbag.
yeah, thank you, beanbag. It's not even like holes. There's squares on the ground, right? And if I throw a beanbag and it lands in one of these, I get some points. If it lands out here, I don't get it. So if I'm just like throwing them, I only count the ones, I don't count that one, I only count the ones that actually fall in this game area, right? What's the probability if I'm just like not even trying, just throwing them that way, that I get it in there? It's going to equal to the percentage of area that is of the whole thing. Because what percent of them would fall there. If I'm just throwing them, it's going to cover the whole area eventually. If I'm just like randomly,
Kick it.
right? Let me headbutt it. There's no spot it would be more likely to land on, even especially if I'm like running around and shit, throwing it around from this side. You with me? So it's going to land anywhere equally likely. There's no reason it would land anywhere specifically more likely. If I'm like all over the place. You guys with me? So it's probably I get one in this spot. It's equal to the percentage of the area that is, right? So if I said the whole area was 1, and this was like 20% of the area, so that's 0.2. What's the probability of getting that square? 20%. It's equal to the area of the region I'm thinking about, that I want to get. If the whole thing is 1, the probability of any little piece is equal to that area. That is the visual component to probability, whereas we know the computational part's kind of gross. So if I can represent something visually for probability where the whole thing is 1, the question about what the probability of any little piece of it is becomes an area question. An area normally is pretty easy. So for example, I don't know if you guys are fully with me, but maybe we do. Let's hear. This is exactly the kind of problem we're going to see at the beginning of chapter 5. Sure. So, has anyone ever... I always think about this. Anyway, I was somewhere, a different city, and I was running to get the shuttle to the airport, and I missed it, just barely. And that meant I had to wait another 15 minutes, because it came every 15 minutes. Are you with me? So, if you arrive and it's not there, and there's no like sign saying how long until the next one, you have no idea if you just missed it or if it's just about to come. Are you with me? So if you arrive just at a random time and nobody else is there, you can't, and there's no sign, what's the likelihood? Is there any more probable amount of time you have to wait compared to anything else? You have no idea. You might have just stepped in, it just pulled away, so you have to wait 15 minutes, right? Or you might have just stepped in right when this other one's about to turn right up to you, and then you have to wait 0 minutes. And anything in the between of there, none of them's more likely. So this is, what is the word uniform? When I say uniform, of course, what do you think of? I love it. Yeah, exactly. A uniform. So a uniform, what is it? Everybody gets the same outfit. So uniform probability is everybody gets the same probability. So what this would look like if it's a shuttle bus, what kind of word is that? Shuttle bus every 15 minutes. I really want you to understand this. I have no idea when I get there, or even if I do, there's the probability. So if I get there and it's just leaving, I've got to wait 15 minutes. Or I could get there right when it's pulling up, I've got to wait 0 minutes. Right? And anything in between those could happen equally likely. So what does it look like as a probability distribution? A big ass box, right? This is going to be the same height for everybody. So it's like a histogram, but not a histogram really, because this is continuous. I don't have little rectangle pieces. It's continuous throughout. How are we doing so far? So there's a lot of stuff that is uniformly distributed just because nothing is more likely than anything else, so they're uniformly distributed. So here's the almost too beautiful thing to believe about this. Any question I ask is based on finding the area of that region that the question sets up. So first thing is, can anybody tell me, what did I keep saying has got to be true about the whole area for this to become probability? The whole area has to be 1. That's the same thing as the sum of all the probabilities is 1. How do I make this area 1? What's the height got to be? What's the width? 15. So what's the height got to be so the area is 1? What do you multiply 15 by to get 1? You multiply by its reciprocal. Yeah. So now I have set up this situation, I have represented it visually, and I made the area 1. So now if I ask a question, and this is where people kind of don't really believe me, but it totally, once you get it set up, you are golden. What's the probability that I have to wait from 6 to 9 minutes? Can you draw that in here? Roughly, right? So 6 to 9. What's the area of that? Do you see the? Do you see? This is what it's been leading up to. Can you see? So it would be. What's the area of that? Well, what's the width of that little blue region? What's the width? 3. What's the height? Always 1/15 for this problem, right? So it'll be 3 times 1/15. 3/15, which is 1/5, which is 20%. So if you arrive at a shuttle bus location, there is a 20% chance you have to wait from 6 to 9 minutes. Anytime you have a uniformly distributed probability situation, you can do this. It's beautiful. It's just based on areas of rectangles. That kicks so much ass. Okay. So a couple more questions. One more straightforward one. What's the probability that it's 1 up to 11.5? What's probably have to wait from 1 minute to 11 and a half minutes? So you do the same thing. The main picture can never change. What I always get is somebody does this. They redraw it. So they only have a box. That doesn't make any sense.